Okay, so um again, all I want to do is just do like a quick overview of from lesson one to the final lesson. I'm not going to go super in detail, just go through like the formulas, the main concepts, the theorems that we saw. And if you want, again, feel free to stop me if you need me to like repeat something or re-explain it. Okay, so okay, let's do it. So let's see if I can condense an entire course into an hour. Okay, so we first started with the concept of limits, and limits is basically the entire basis of calculus because you cannot understand the concept of a derivative or of a definite integral without limits. Notice that when we learn those things, you need a limit to prove that concept. So that's why limits is the foundation. So limits is different from anything you've learned before because you're used to learning like, if you have a function and you input a value into the function, the output gives you, basically this is the point. This gives you the ordered pair 5, 7. So you can like understand that that's a point on a graph and so on and so forth. But with a limit, the concept is totally different because you don't care about what the value is at that value of x or t or whatever the independent variable is. You care about what it approaches, okay, the value that it approaches. So approaching is very different from equals, two completely different concepts. Similar, and most of the time they are the same, but there are cases, most particularly in like piecewise functions, um, where it does make a big difference. So again, the limit notation was like this. And again, this here is the function. This here is the value of x to approach. And the solution to this is the value that it approaches. Again, not the value that it is. So just because this is true doesn't mean that this is equal to f of c. That's not guaranteed. That's not guaranteed by a limit. Okay. So that's why what you care about is what it approaches. And the only way to do that is either with a table or to look at it graphically. Those are like the only two like legit ways to figure that out. Okay. Now keep in mind that this here is called the common limit. This is the common limit. And the common limit only exists if you approach the same value from left and right. So of course, if you have this here as you approach the limit from the left, and as you approach the limit from the right side. Okay, so the common limit only exists if the left and right approach the same value. Okay, so I mean, it's pretty easy to prove graphically. Like again, if you have something like this, and this is function f of x, here, notice that f of 4 does not exist. Okay, because there's a hole there. Okay? But if the limit as you approach 4 of the function, this would approach, right? This approaches 3. Okay. Again, when you're doing a limit, you don't care what the actual value is at x equal 4. You just care about what it approaches. Okay. And we can say that the common limit equals 3 because from the left and right, we're approaching the same value. Okay. But if you had something like this, though, See, this is an example of a very weird one. So here you have a function, okay, and this function is defined for all values of x. Okay, so all the domain of this function is all real numbers. But it's a little weird. It's acting very strange at 5. So so if I were to ask you what is g of 5, what would that be equal to? Right, is 3, right? But now the limit as x approaches 5 from the left, what value of y is the function approaching as you approach 5 from the left? And as you approach 5 from the right, it approaches 4. So what would the common limit be then? Right, does not exist, or NA, or whatever. You could, these are most likely multiple choice questions. They would accept any of those responses. So yeah, the common limit doesn't exist because both left and right don't approach the same value. But anyways, that's kind of like the basics. And of course, you can do the same thing with a table. So I've seen before problems where they give you a table and you just have to look at the table to figure out the values that it approaches. Now, most of the time, direct substitution does work. Most of the time, you do learn about direct substitution, which is that most functions don't have any like problematic issues, right? So for most cases, you can plug in the value of x into the function, and that value is the limit. Because for example, polynomials, which have like a very smooth and continuous graph, there's no problem there, right? Basic things like rational functions where there's not a vertical asymptote, those work. Radicals in their domain, other functions like that, like basic functions, don't have problems. Really, the time when you have to start being really careful is when you run into like piecewise functions, because that's where you have to kind of play around with them and see what's happening with the piecewise function. But most of the time, you can just do direct substitution. Okay. Now you do have cases where you do direct substitution and you get like 0 over 0 or infinity over infinity when you plug them in. Those are indeterminants. Now, we had learned that you could do algebraic manipulation to solve those, but you really don't have to do that anymore because since we learned derivatives, there's the L'Hopital's rule. So I'm going to skip that for now because you really don't have to waste your time doing algebraic manipulation, okay, which is like factoring and all that, and canceling out that common factor. But normally when you get this, that's because you have a hole, okay, on the graph. So because it's just that one value of x that you have a problem. So the graph, it's not a vertical asymptote. It ends up just having like a hole in the graph. Or another word for a hole is a removable discontinuity, because with algebraic manipulation, you could remove that hole. Okay. So the types of discontinuities that we've seen, types of discontinuities. You have your removable. Did I spell that right? Whatever. That's like a hole. Okay, so again, that's when you have something like this. Even this would be considered a removable discontinuity because again, you still have a hole in the graph. So anytime you see a hole, that's a removable discontinuity. Of course, you have your infinite discontinuities, which, what's an infinite discontinuity? Anyone remember? So like it's a where the graph splits and goes to infinity. What do you remember what that's called? Yes, right, a vertical asymptote. Yeah. So basically, if you have something like that, Obviously, that's not continuous. It goes to infinity, the point doesn't actually exist there. So that's what you can either call it a vertical asymptote or an infinite discontinuity. Both are the same. And of course, the last type of discontinuity that you can have is a jump discontinuity, which, let me say this is a whole, this is a vertical asymptote. And a jump discontinuity is a gap. So that's when you have like that, okay? So those are your three types of discontinuities. And speaking of continuity, the definition of continuity is that the limit of a function is equal to the value of y at that function, okay? So most of the time, these are like multiple choice, and they just ask you, is the function continuous? All you have to do is prove, like, just try to figure out, is the limit exist, the common limit, and is the value of y the same? Right? That's how you can determine if a function is continuous. If this were a free response, you would have to, again, show the steps. So again, in order to prove the common limit, you have to do left and right. So like on a free response, you'd actually have to show limit from the left, limit from the right, and that is equal to the function at x equals c. And then if you can prove that, then you say, therefore, the function is continuous. So if this was a free response, you'd actually have to show the steps. You have to show that this statement is true. That's how you would prove that a function is continuous. Okay, so that's why what we saw before, the discontinuities, those are not continuous because they don't satisfy the continuity. Most of the time, these are just piecewise. Like, again, if you have something like this, it's going to make this up. Let me see here. Hold on. I'm just making this up here. Right? So they would give you this. So first of all, like if this was a free response, you'd say, okay, first I have to determine what's the value of y. So f of, I'm sorry, I meant to say 1. My bad. Again, forgive me, I haven't used this feature for a very long time. Okay, so let's say the question is f of x continuous at x equal 1, right? So you would have to prove that. So you'd have to say, okay, first of all, what's the value of y of the function? That's the easiest one to do. So what is f of 1? So again, because it's equal, oh no. Because it's equal at x equal 1, at x equal 1 is equal to the second function, you plug 1 into the second piece, which would be 5, right? So that's the value of y. Then you have to do the common limits. You say, okay, limit as x approaches 1 from the left. Well, you can do direct substitution, but which is the piece that exists to the left of 1? This one, because that's the piece that exists to the left of 1. If x is less than 1, that means that the domain of this first piece is from -infinity to 1. So that's where you would do the direct substitution in. So you'd get 1 squared minus 3 times 1 plus 7, which would be 5. And then the limit as x approaches 1 from the right, you can do direct substitution into the function on the right, which would be 5 times 1, which is 5. Hence, the limit as x approaches 1, the common limit, because left and right approach the same value, it's 5, which is equal to f of 1. Therefore, Yes, it is continuous. So if you were to graph this, you'd see that the graph would kind of do something like, I would imagine something like that, so they do meet at that point. So the limit and the value of y are the same. And that's how you can prove that a function is continuous. And if any of these things fails, then you just say not continuous. Okay. So that's how you can prove continuity. The only other two things we have to just talk about with limits, because those are tricky ones, but again, most of the time they're graph problems. So if you know how to analyze the function graphically, this shouldn't be that difficult, is with the asymptotes. Okay, so again, vertical asymptotes occur when only the denominator is equal 0. Okay, so if you have a function here, right, and you end up getting 0 divided by any number, right, when you do direct substitution and you end up dividing only by 0, that means you have a vertical asymptote at that value of x. So really, the only way to determine which way it's going is just test a point. Like that's really the only suggestion I would have there. Again, if this is a graphing calculator section, graph it, see what happens graphically. But if it's not a calculator section problem, just plug in a random point and don't even calculate the actual value of y, just determine if the answer is going to be positive or negative. And that's all I would recommend. So for example, if you had something like this, so, and you are asked to solve, let's say, I'm sorry, from the left. Let's say from the left. So first of all, with any limit, first thing you should always do is just do a direct substitution, see what happens. So if we did direct substitution, we would get 10 minus 3 over 5 times 0, which would give us 7 over 0. So that means this is not an indeterminate. Indeterminate if it was 0 over 0. But just because the denominator is 0, you have a vertical asymptote. So what I would do is I would just test maybe like 1.9. Okay, that's probably what I would test. So I wouldn't even waste my time calculating the value because obviously I know it's going to go either up to infinity or down to negative infinity. So all I would do is just determine, will the sign of the value of y at x equal 1.5, 1.9 be positive or negative? So if you plugged 1.9 into the numerator, I would get a positive number, right? 1.9 plus 3 would be positive. 1.9 minus 2 would be negative. So that means I'd have a positive over a negative, which is negative. So that means I would know that the solution to this would go to negative infinity. Okay, that's because at 1.9 I have a negative number. And again, vertical asymptotes, as you get closer to that vertical asymptote, it's not going to change direction. You can kind of tell from pretty far away the direction that it's going to go. So essentially what's happening with this graph is it's going like that from the left. Okay, so because you're seeing at 1.9, and this is 2, that you have a negative value of y. So it's obviously just going to keep going down. Okay, so that's how you could determine the direction in which you're approaching a vertical asymptote. Okay, so if the limit approaches a vertical asymptote, the answer will either be positive infinity or negative infinity. But again, if you're doing a common limit, the common limit of a vertical asymptote can exist only if both ends go in the same direction. So if they both go up to infinity or if they both go to negative infinity, then the common limit exists. But if they go in separate directions, here, the common limit would not exist at 2. But if they did this, right, if they both left and right went to negative infinity, then the common limit would be negative infinity. Okay, so that's how you can tackle vertical asymptotes. Okay. And the last one is horizontal asymptotes, which is if the ends go to that's end behavior. Horizontal asymptotes is end behavior. So that's if the limit goes to infinity, you have to determine what happens. So this one's a little trickier because again, when you're doing infinity is not really a number. So you can't really like technically plug in infinity, like directly substitute infinity. But you can like just conceptualize the concept and be like, okay, infinity is just a big number. So you can kind of just by looking at the function, determine how it's going to behave. So like, for example, if you have something like this, right? You could see here, okay, if I were to directly substitute infinity, which technically you can't do, but you can conceptualize, a massive number minus 5 is still going to be a massive number. So if the denominator gets bigger, what happens to the value? Do you know what this would be equal to? Right, 0. Yeah. Basically, if you divide by infinity, or the bigger the denominator gets, the closer to 0 you get. So that would approach 0. Right, very good. Or if you had something like this, exits to negative infinity. Like something like that. If you were to, again, directly substitute a negative big number, quote unquote, you could see here, you'd get, well, with polynomials is a little different. You just really have to look at that leading term because that leading term is growing so much faster than this, right? So you can kind of just ignore those. And you could see here, when you square a negative giant number, you're going to get a positive giant number. So because this is the values of that first term are growing so much faster than the rest, you could ignore the rest and just say this goes to positive infinity, right? Now, when you get more complicated ones, most of the time you'll get infinity over infinity. So you could do L'Hopital's rule, especially if the function is really complicated. But if you're dealing with a basic rational function, you actually don't have to waste your time with L'Hopital's rule because again, L'Hopital's rule always works. So if you forget what I'm about to show you, that's fine. You can still do L'Hopital's rule to remember it, but there's a little shortcut when you're dealing with rational functions. And that is, if you remember, a rational function is two polynomials divided by each other. So really, you can determine the horizontal asymptote by looking at the degree of the numerator and the degree of the denominator. So basically, so I'll say here, where f of x and g of x are polynomials. So basically, if the degree of f is greater than the degree of the denominator, you would say that there's no horizontal asymptote. So that means the answer would either be positive infinity or negative infinity. Okay. If the degrees are the same, then you would just divide the leading coefficients. LC stands for leading coefficient. And then if the degree of the top is less than the degree of the denominator, then the horizontal asymptote would be 0. So I don't know if you remember that. I also taught that in algebra 2 as well. That's kind of like a little trick to help you when doing a rational function. So again, if you forget this, it's not the end of the world. Again, L'Hopital's rule will help you to determine what that answer would be. But sometimes it might get really complicated to do L'Hopital's rule. You might have to do it like 3 or 4 times to find the answer. So in my opinion, it's just easier to remember this rule. But again, that's totally up to you guys. Okay. 2 more things and then we're done with limits. The last thing here is the squeeze theorem. This one's very rarely asked, but you technically do need to know it. So the squeeze theorem is basically, the concept is, let's say you have 2 functions here. Let's say you have f of x here, and then you have g of x here. You have g of x here, okay? And then you have a function h that is always going to be between those 2 functions, okay? So basically, if the limit of f and g approach the same value, let's say that this is c. Let's say f and g approach the same value, right, as you approach c, okay? But you have a function that exists between them at all times, then you could just kind of, I mean, it's kind of an obvious thing when you look at it. A lot of these theorems, I don't know if you've noticed, they're like obvious, but you have to put them in words because they're obvious because they're always true. So like, again, when you're asked to prove something, you state the theorem because it's a truth, right? And that's how you can prove. Anyways, if you have another function h that exists between them, obviously that function would have to approach the same value. So that one we could do one in practice if you want to do one, but this one's a pretty straightforward one. I don't have time to write out the proof, but again, in words, you basically say, if a function h exists between f and g, so basically h is less than f but greater than g, and f and g approach the same value as they approach c, h will approach the same value. So that's called the squeeze theorem or the sandwich theorem. Some people call it the sandwich theorem because you're basically sandwiching a function between 2 other functions. That's the squeeze theorem, okay? And then, of course, the last one was the intermediate value theorem, which is tied with the concept of continuity, okay? So what that states, and again, it's like another very obvious statement. Like, obviously, when you look at it, it's like, duh. But if you're asked to prove it, you just say it's true because of the theorem, and it's obviously going to be true. So if you have a function here, and this, of course, would be f of a, and this value of y would be f of b. So basically, if f of x is continuous, okay, this one, the key to the intermediate value theorem, let's say IVT, the key to the intermediate value theorem is that the function is continuous, and there's one more important thing, and f of a does not equal to f of b. These are 2 key things, okay? For the intermediate value theorem to be true, the function has to be continuous, and the beginning and end of the interval cannot be the same height. They have to be separate heights, okay? If those 2 things are true, then it is guaranteed, basically, like, to put this in simple words, every single value of y from f of a to f of b is going to be covered at least once. Like, if it's continuous, there's no gaps, there's no asymptotes, there's nothing crazy happening. So basically, no matter how crazy the function is, every single value of y from f of a to f of b is covered. That's all the intermediate value theorem is saying. But of course, to put that in proper terms, you'd say it is guaranteed that there is at least one c that's between a and b such that f of c is between f of a and f of b. Right? So that's like the technical, like proper way of expressing that concept. But in just brutal or brute terms, like just straightforward terms, it's every value of y from f of a to f of b is covered. That's basically all the intermediate value theorem is saying, which is, again, if a function is continuous, that's pretty obvious. Okay. So that's the intermediate value theorem. Okay. And that's the basics of unit 1, which was limits. Okay. Then now we go into derivatives. Okay. And you can't prove a derivative without a limit. I'm not going to go into the proof of derivatives, but I will say this. The concept was, again, you've only ever known how to find the slope between 2 points, right? So if I gave you 2 points on a function, you could tell me very easily what the slope between those 2 points are, or is, because again, you just do the change in y over the change in x, right? So you do y2 minus y1 over x2 minus x1, right? That's how you would find the slope with 2 points. But calculus wants to prove the question, what is that instantaneous slope? What is that slope at 1 point? What is the slope of the tangent line? That's the question that calculus wants to answer. So the setup for this is basically like, yes, we are going to find the slope between 2 points. So if I have here x, and then I have here a point x plus h. So meaning here the distance is h. Okay, so obviously the value of y here would be f of x, and the value of y here would be f of x plus h. Obviously, I can find the slope between those 2 points pretty easily, right? That would be, the rise would be the change in y. So f of x plus h minus f of x. And the run would just be h, right? Because that distance from here to here is h, okay? So that's the slope between those 2 points. But now, if you make h approach 0, again, listen to the key word, approach. You can't make it equal 0 because then you're going to get 0 divided by 0, which is, of course, an indeterminate. But if you make h approach 0, you can kind of visualize that as this point gets closer and closer to this point, the slope of the secant line is going to approach the slope of the tangent line. So if you make h approach 0, that value will give you the derivative or the slope of the tangent line. So this here is, of course, the formal definition of the derivative. Okay. And you needed a limit in order to prove that. So that's why, we first started the year with limits. So this is the formal definition of the derivative. And of course, I should actually specify this is equal to f prime of x. Okay, that's the notation that you would use. That's, I think, Lagrange notation is the name of that. You also have the alternative definition, but that's used when you're just trying to find the slope of the tangent line at 1 point. So if you're trying to find the slope at x equal a, or the derivative at x equal a, let's just say the derivative. The formula for that would be, as x approaches a, you'd have f of x minus f of a over x minus a. Okay, and if you've solved that limit, that will give you the slope of the tangent line at x equal a. So that's the alternative. And the first one is the formal. Oh, darn it. This is equal to f prime of a, right? So that's your alternative definition. Now, just to say this, and we saw this a little earlier, now that you know L'Hopital's rule, technically you could use L'Hopital's rule if you really want to solve these limits, okay? But you can also, if you understand that these formulas here represent the derivative, you don't have to do L'Hopital's rule. You can just use basic derivative rules. So you don't actually have to solve the limit. That's kind of like the punchline. Remember, I first taught you guys how we would solve these as limits, but then you realize that there's a pattern that's always showing up, right? And then those patterns lead to formulas that you can just memorize. So you could solve the limit, but if you understand that this just represents a derivative, you would just use the derivative rules. Okay, so that's, but you need to be aware of these formulas. You have to know them. So, but anyways, obviously, this is how you find the derivative. But as I said before, there are these rules or these patterns that show up and they're always going to work. So instead of learning how to solve the limit, just memorize the patterns. And those are the formulas that you need to know. So let's go over all the basic derivative rules that you need to know. Okay, so basic derivative rules. So first of all, oh, and remember, there's also the, oh my God, there's Leibniz notation. I forget the name of them, but of course you had this to represent the derivative function, or you could say this. These represent the same thing, or dy dx, or y prime is also acceptable. So those are really the only two notations you need to know to do derivatives. In more advanced calculuses, like in Calc 3 and stuff, you're going to learn other notations for derivatives. And Newton's notation is not used. That's like an engineering concept, but nobody really uses that. So anyways, you just need to be aware of that notation. Okay, so anyways, let's go over the basic rules. So the derivative of a constant is literally just 0. Because obviously a constant is a horizontal line, so the slope of a horizontal line is 0. Okay. The derivative of a polynomial with any exponent is always going to be, basically the trick is you bring the exponent out and multiply it, and then you subtract 1 from the exponent. Okay, again, this is only true for polynomials. Okay, if you have a constant multiple, you can just multiply the constant to the derivative of the function. Okay. The derivative can be distributed only if you add or subtract. Because this is f prime plus or minus g prime. So that is acceptable. So those are like the basic rules. Okay. So those are like the ones that are very simple. And by now, I hope we don't have to go over that. These are very simple rules. Okay. So these should be ingrained. Okay. Then, notice that, we have the sum and difference rule, which is just you can distribute the derivative. Obviously, it gets a little bit more advanced when you're going to be doing the product or quotient. So those you can prove, they're very complicated to prove, but at the end of the day, there is a formula that follows a product and quotient. Okay, so again, let me just be very clear because I still see it happen. That when people see a product that they're like, oh, they say, oh, this is equal to f prime times g prime. No, this is wrong. You cannot distribute a derivative when you multiply or divide. You can only do that with addition or subtraction, but you cannot do that with multiplication or division. So unfortunately, you have to memorize the rule. Hold on one second. Let me move this over to have more space. Okay, you have to memorize the rule, which hopefully by now you have memorized. The way I like to remember it is I get the derivative of the first one and multiply by the second function. Then I add the derivative of the second function and multiply the first one. So you kind of like flip-flop the derivatives and multiply. Okay, that's the product rule. And then for the quotient rule, it's actually, I like to think of it as the same setup, but instead I subtract, right? So I'm going to do f prime times G minus G prime times F. So notice it's like the same setup as the product rule, but you're subtracting, but then you have to divide all of that by the denominator, not the derivative of the denominator, the function denominator squared. And that's the quotient rule. Okay. Then of course, what else? Then you are allowed to do second derivatives, third derivatives. All that means is you just do the derivative of the function. And then you do the derivative of what you just got. Then you can keep doing the derivative of what you got. Okay, so then of course you have the chain rule, okay, which is what do you do when you want to get the derivative of a composite function. Okay, so that is okay, so what you do here is you multiply you get the derivative of the outer function, leaving the inside alone, and then you multiply that by the derivative of the inner function. So that's the chain rule. And that's how you tackle getting the derivative of a composite function. Then we also have this is the last main one, which is the derivative of the inverse function. Okay, which was 1 over f prime. So, and that's the last one. Okay, so with these rules, you can now solve basically the derivative of literally any function, because these are the only types of things you can have. Of course, there are the more unique functions. So I'm going to go ahead and show you the last ones. You have, I'm not going to write them all down, but you should have them memorized. You need to know your trigs. Well, actually, you need to know the derivative of ln x is 1 over x. You need to know that the derivative of e to the x is e to the x. You need to know like the basic ones, sine and cosine. That's cosine x, and that's negative sine x. So, and then of course, from these, actually, if you use the product rule, I'm sorry, if you use the quotient rule, and you know sine and cosine, you can find the derivative of all the other trig functions. So you need to know basically all 6 trig functions and inverse trig functions. Okay, so that's pretty much it. Those are all the derivatives you need to know. Okay, so that pretty much summarizes that for all the derivative rules, both easy and advanced. Okay. Am I missing anything? I think that's the basics of all the derivatives. Is there anything I'm missing, you think? I mean, I think that's pretty much it. And of course, you had the power rule, which is in the previous slide. After you know how to do literally any derivative, now you can apply them to real world applications. Okay, so of course, hold on. Give me a second here. God, this is so much information. But like it's a lot of information, but like we've practiced it so much that hopefully a lot of these things are already like just ingrained in your brain and you don't have to memorize it because you've done it so much. But yeah, it is a lot of information. Okay. But after you know how to do any derivative, now is the applications. So first thing you got to know is, of course, when you hear the word instantaneous, that's just the derivative. Okay. If you're asked for average rate of change, that's the secant. That's where you have to find the slope between 2 points. So if you're asked to find the average rate of change, that would be, but if you're asked to find the instantaneous rate of change at x equals c, that is f prime of c. Okay, that's just like that instantaneous rate. So that instantaneous slope at c. Then of course we had PVA problems, your position, velocity, acceleration. So the rate of change of position is velocity, and the rate of change of velocity is acceleration. If the velocity is positive, that means you're basically, there's different, depending on the context of the problem, it might mean different things. So it could either mean you're moving forward, you're moving up, you're moving right, like whichever, like, because again, velocity represents the rate of change of position. So that means position is growing, right? So if like you're on the x-axis, if the values of x are growing, that means you're moving to the right. If you're moving on the y-axis, if the values of y are growing, you're moving up, right? So it kind of depends on the context of the problem. And of course, if the velocity is negative, that means you're going backwards, left, or down. Like again, all depending on the problem. And if the velocity is equal 0, that means you're stopped. Okay, so you're not moving. And then of course the acceleration. Okay. The acceleration is the tricky one. Okay. So obviously, acceleration just tells you how the velocity is changing. Okay. But to determine if an object is speeding up or slowing down, you also need to know the velocity as well. Okay. So this is where it's tricky. So again, a positive acceleration means that the velocity is becoming more positive. And a negative acceleration means the velocity is becoming more negative. But this is where the context matters, because of course, if the velocity is positive, that means you're moving forward. And if the acceleration is positive, that means the velocity is getting more positive. So it's actually accelerating. But if the velocity is positive, but the acceleration is negative, that means that the velocity is getting less positive. So that actually means you're slowing down. But if the velocity is negative, that means you're basically moving backwards. So a positive acceleration means the velocity is getting less negative. So you're actually slowing down, but going backwards. But if the velocity is negative and the acceleration is negative, that means the velocity will get more negative, meaning it's actually speeding up backwards. So what you have to remember here is, this is the weird one with acceleration. If sine of velocity and acceleration are the same, you would say that the object is accelerating. But if the sine of velocity and acceleration are opposite, you'd say that it is decelerating. Okay, so that's kind of like the weird one with PVA problems. Okay, so it all matters. It all depends on the context of the problem. So you really have to pay attention to what's happening. But remember, a negative velocity just means you're moving backwards. So if your velocity is getting more negative, that means you're accelerating backwards. That's so again, it just depends on the problem. Okay, so that's the basics of PVA problems. Okay. Oh, one thing I did skip was implicit differentiation, which you do need to know in order to do like related rate problems. But implicit differentiation is just you really just have to assume that y is equal to like f of x. Like they're always going to say that if when you read the multiple choice sections or like any sections, you're always going to say assume that y is a function of x. They always say that. Okay. So that's why you're allowed to do like implicit, unless otherwise stated. Unless otherwise stated. So that means if you have something like this, this would actually require product rule. Because if you want to now get the derivative with respect to x is a function of x and y is a function of x. So you have two functions of x multiplying each other. So you would have to do product rule, right? So just to kind of quickly show you how that would work, the derivative of the first function, the derivative of x, this is like saying derivative of x with respect to x times y plus the derivative of y with respect to x times x equals to the derivative of 5. So at the end, you get 1 times y plus x times dy dx equals 0. So that's basically like what the implicit differentiation is. It's like if the function is too difficult to like isolate. This one, I mean, you could have just solved for y too. You could have said y is equal to 5 over x, right? Or 5x to the minus 1. And then you could have done just basic differentiation, right? But obviously, you might get functions or equations that are very complicated, where it's very difficult to isolate the y. So it's just easier to just implicitly differentiate and just differentiate both sides with respect to x, um, and just treat y as a function of x. And that's like the shortcut. You know, the only other trick one here is, of course, like if you have, you know, y to the 7th, again, y is a function of x, and it is the composite of the function raised to the 7th. So this is a case where you would need to use, actually, let me do this, where you can do implicit differentiation. So you could say 1 over, what am I doing? 7 times y to the 6th, but then you have to multiply that by the derivative of y. Because you're doing chain rule, you have to multiply by the derivative of the inner function. And this would be equal to 3x squared. Right. So then dy dx would be 3x squared over 7y to the 6th. Right. So that's basic implicit differentiation. So that is important in order to do related rate problems, which is, again, if you have a system of a bunch of things changing at the same time, and of course, the rate of change of one thing affects the rate of change of the other thing, literally the rates are related to each other. Hence the name related rate. So you just have to assume that all of those changing variables are functions of time. So you would do implicit differentiation. It's too difficult to do one like right now for the review, but we'll definitely do some practice problems a little later. Okay. But yeah, the last main like big application one is related rates. Okay. Then of course we talked about function and graph analysis, which you also need to know derivatives to do. So in that section, we learned the concept of extremas. Okay, so you have two types of extremas. So you have relative extremas. Okay, other people call, you might see instead of relative that some people say local. So it means the same thing, local extremas. So both are correct. Okay. So basically all that means is you're actually not looking at the function as a whole when you're determining relative and local extremas. You're just looking, this is why some people call them local extremas, because you're really just looking at like a specific localized area. Okay, so if the value of y is the highest or lowest value in a certain area, that's your relative or local extrema. So that's basically, I like to think of these as basically your turning points. Okay, so basically, again, this or sharp turns. Sharp turns are also included. Okay, and these occur at critical points. Again, where the derivative is equal to 0 or undefined. And f is defined. So basically the point has to exist. So it can't be a hole, it can't be a vertical asymptote. Those are not included as critical points. Critical points are defined points where the slope is 0 or undefined. So that's why all of these are relative or local extremas. And then of course we have our absolute. There's another name for absolute. Absolute. There's another name for it, but nobody uses it. Absolute is the main one. Absolute extremas. Which this is when you look at the function as a whole. Okay. And you look which is the highest value of y or lowest value of y. Okay. So those are that the absolute extrema is like as a whole, where do you find the most the highest or lowest values of y? So this here is candidates are relative extremas and endpoints. Okay, so basically, to determine an absolute extrema, you have to look at all relative extremas and the two endpoints. Okay, and you test all those values and determine which of those will give you the highest value of y or the lowest value of y, and those would be your absolute extremas. Okay, so endpoints are candidates for those, for the absolute extremas. Okay. Now, we already talked about critical points. You can also determine here. Now, this is the key stuff here. If the derivative is greater than 0 in an interval, or no, for all x, then what could you say about the function if the derivative is positive for all values of x in an interval? What does that mean? Right. Right. Okay. So that what that means is all the tangent lines have a positive slope. That only occurs if a function's increasing. And then of course, if all the slopes are negative for all x in an interval, you'd say it's decreasing. Okay. With this, you can actually determine if a critical point is an extrema. So this is the first derivative test. This is important here. So basically, if how do I word this? At a critical point, if f prime goes, I'm sorry, goes from positive to negative, that means you have a relative max. And if it goes from negative to positive, so negative slopes to positive slopes, that means you have a relative minimum. Okay, so that's called the first derivative test, because you know that there's a critical point, and you're basically saying if the derivatives change sign, you could determine if it's going to be a relative max or min. And if the signs don't change, it's neither. Then neither. So that might mean that you have like a horizontal inflection point or a vertical inflection point. Okay, so it kind of just depends on the problem. Okay, so those are your that's the first derivative test. Okay, then that leads us into the second derivative, which is now, if you think about it, the rate of change of the rate of change. So the rate of change of the slopes. Okay, and depending on how the slopes are changing, that determines the shape of the curve of the graph. Okay, so if the second derivative is positive for all x in an interval, what does that mean? Perfect, right? That means it is concave up, meaning it has a shape like this. And again, you could see that there are like tangent lines, but as you move to the right, the tangent lines are, I'm sorry, this is concave down. What am I talking about? Concave up. Sorry. You can see that the slopes are actually increasing. So even if you have a negative slope, if you get less negative, you're increasing, right? And then if the slopes are getting steeper and steeper, right, the slopes are increasing. So the graph then takes on that kind of curvy shape that goes like in an upward direction. And then of course, if the second derivative is less than 0 or negative for all x in an interval, then you say it's concave down, and you can see the slopes are decreasing. They're either getting less positive or becoming more negative. So it starts taking on that curvy shape. And determining graphically if a function has concavity, I like to use my hand test. So if you're to put the bottom of your hands on the graph and like cup the graph, if your hands are pointing upwards, you could say it's concave up. And if your hands are cupping downwards, it's concave down. That's my personal trick. Okay. Let me do something here. Let me actually do this here real quick. Give me a second. Just to kind of carry on the concept, the conversation. I'm going to delete that. Hold on, how do I do this? Wait, what's happening? How do I delete? What is happening? Let me move that over to the side. Let's pretend that's not there. Okay, let's move this up. Okay, so kind of continuing on this topic. So if we're talking about concavity, if the second derivative is equal 0 and the sign changes, that means you have an inflection point. Again, unlike a critical point where a critical point exists when the derivative is 0, and it doesn't matter if the sign changes, the sign change does matter for inflection point. It is not considered an inflection point if the concavity does not change. Okay, so an inflection point, the second derivative will be 0, but the sign has to change for it to be considered an inflection point. So that's why when you're determining inflection points, first call them candidates and then test it. Okay, and the ones where the sign does change, those are your actual inflection points. Okay, so you have to be very careful when you're talking about inflection points. Then what else is there? Oh, there's a second derivative test as well. Which there was a trick question like that on the mock exam that I gave you guys, which if you know that there's a critical point, but all you know is a second derivative, you could determine if that's a relative extrema or not. Okay, so basically, if x equals c is a critical point, right? If f double prime of c is positive, that means you have a relative minimum. And if f double prime of c is less than 0, that means you have a relative max. Okay, that's the second derivative test. So they're basically saying you have a critical point, right, where the slope is 0, but in that interval or at that value of x, it's concave up, for example. That means that that's a relative minimum. But if at that value of x, the second derivative is negative, meaning it's in an interval where it's concave down, but it's a critical point, that means it's a relative max. So that's called the second derivative test, and they do want you to know that one as well. Okay, so if you know the critical point, but the only information you have about the function is its second derivative, you can still determine if that critical point is a relative max or min. Okay, so that's the second derivative test. Okay, and that's the basics of function analysis. Of course, then you have your graphs and being able to read the graphs, but that again requires a lot of practice. So that will save for the review. Okay, but yeah, we're running. Oh my God, we've already been talking for like an hour already. We got to start wrapping this up soon. Something I did forget to mention a little earlier was the concept of differentiation. I was thinking about this. I forgot to talk about that. Differentiation is kind of like continuity. Remember how when we talked about continuity, you have to prove that it's continuous by checking the limit and the value of y. Differentiation is very similar in the sense of a function is differentiable only if, one, it is continuous, but two, the derivative is defined. Meaning you cannot have a derivative that does not exist. Okay, basically the derivative has to exist at the value. So first things first, the function has to be continuous. If it's not continuous, you immediately know it's not differentiable. And second, if the derivative exists, so like you plug in the value of x into the derivative and you get a value of like an actual number, then it's differentiable. Okay, so that was differentiability, which I forgot to mention. Also, two other things I forgot to mention because I'm just kind of so many topics. First one was the mean value theorem. Okay, the mean value theorem, again, it's another obvious theorem if you look at it. So So here we have a function f of x, right, in the interval a to b. And of course, this is f of a, and this is f of b, okay? This one's very obvious. Now, mean value theorem is actually the only theorem where differentiability matters, okay? This is the only one where being differentiable makes a difference. All the other theorems, the only condition is that the function is continuous. Mean value theorem, though, is the only theorem where differentiability is important. Okay, so basically what this is saying here is if f of x is differentiable from a to b, then it is guaranteed there is one x, there is at least one, then doesn't mean there has to be one. There's at least one c between a and b where f prime of c is equal to the average rate. So it's kind of an obvious theorem because if the function's differentiable, which means it's continuous as well, of course, and differentiability implies continuity. It is guaranteed that there has to be at least one point. So see, this is f of b minus f of a divided by b minus a. There is at least one value of x where the derivative has the exact same slope. Okay, this is f prime of c, right? So that's what the mean value theorem states. There has to be at least one value of x where the derivative is the exact same slope as the average rate of change between the ends. Okay, that's the mean value theorem. And then the other theorem that I skipped was the extreme value theorem, which goes hand in hand with absolute extremas. This is the theorem to prove absolute extremas. And this is actually, let's do something like this. So basically what this is saying is if f of x is continuous from a to b, it is guaranteed there will be at least one absolute max and min in closed interval a to b. Okay, so basically what this is saying is you are guaranteed one absolute max and one absolute minimum if the function is in a closed interval. Because again, the extreme value theorem basically is telling us that endpoints are considered absolute extremas. That's basically all the extreme value theorem is saying. Okay, so you will have one extreme or absolute max and one absolute min because endpoints can be considered. So you see here, this is your absolute max. Even though that's a relative max, it is also the absolute max, but this endpoint is the absolute minimum. Okay, so that's all the extreme value theorem is stating, that if you're in a closed interval from a to b and the ends are considered, are defined, you will have an absolute max and one absolute min. Okay, so those were like the other two theorems. Okay, and that's it for derivatives. Of course, you had optimization, but optimization's just finding the max or min. The optimization is just finding absolute max and absolute min, but in the context of a real world problem. You're just asked to find what is the absolute max and what's the absolute min. That's all optimization is. Whew, and that's all of derivatives. My God, it's a lot of information. I mean, has this been helpful so far? Or like, meh? I mean, I know it's a lot of information, but now funny enough, it's so interesting. The integral section was so small. It was actually a very small section. It was only, I think, 2 or 3 units, but half of the test is integrals. Um, so I'm not going to go super crazy into integrals. I'll just go ahead and show you the formulas, but I personally need a break right now. I have been talking for like an hour and 15 minutes. So let me take a quick break. We can get this done in 20 minutes, and then you'll know everything you need to know about derivatives. Oh, I did yesterday, but but, um, but no, not right now, not while I'm on the job. Um, but yeah, let me take a quick break. Let me go use the restroom. I'll be back in like 5 minutes. I'll review integrals, and then we're just gonna do practice problems. Okay. I will be here till 2, so you can stay as long as you want. Okay, so I'll be back recording. Okay, so now integrals. So I mean it's really weird because like the AP, they they actually teach the definite integral first and then teach antiderivatives. But I don't know, to me, like when I was in college, I remember learning antiderivatives first and then applying it to the definite integral. But so that's the way I teach it, because in my opinion, I think it makes more sense. Because if you know how to do an antiderivative, you can then do the fundamental theorem of calculus, and it's like easier. But that's my personal opinion. So that's why like around this time, the units I did in class were a little different than the units that you would see in AP, because they do it in a different order. That's really the only difference. So um I had talked about first the indefinite integral, which is basically the process or the operation to find the antiderivative. Okay, so basically, if you have a function like that, okay, this is how you have to set it up this way. Again, if you forget to put that dx, I'm not 100% sure, but I think you might lose a point if you forget to put that dx. This is called the variable of integration, kind of like when you do the derivative of function, right? Like if you have f of x, you would do d dx, right? To say you're going to get the derivative with respect to x. If this was f of t, you would say d dt, right? Because you have to specify, I'm going to get the derivative with respect to function, to variable t. So it's the same thing here. You have to specify what variable you are going to find the antiderivative with respect to. So if this was f of t, why is this not? You would have to say d dt or dt. Okay, so you have this, all of this goes away once you find the antiderivative, but this is how you like set up the operation to find the antiderivative. And of course, this would be equal to f of x plus c, right? Always, excuse me. Um, always put that plus c, because again, when you get the derivative of a constant, it becomes 0. So you can't assume that there is no constant, because obviously if you get the derivative of this, it should take you back to that. And obviously the derivative of the constant will go away. So, so you always have to include that constant of integration. If you don't put that, you will lose points, okay? And again, you might see it like this, where if they give you f of x, this is just a notation, but like obviously the antiderivative of the derivative is the function. But the antiderivative function, the way you can show that as an antiderivative is with the capital. So it's the same thing. It's just like another notation that they use to show the antiderivative. And you need to remember this here is called the this is called the general solution. The reason this is called the general solution is because you have that plus c. So that plus c could be anything. So like in general, this is what the solution would be. Okay. But an initial condition, I'm sorry, a particular solution can be found if you know a particular point or an initial condition. So with an initial condition, C can be solved for to find the particular solution. Okay, so I mean that's pretty. So basically, if you know a point, literally plug the point into this function and solve for it, and then you could solve for C, and then you know what the particular solution is. Okay, so basic antiderivative rules would be, let's see, the antiderivative constant. Actually, let's use K to not confuse this. This would be Kx plus C. Let's see here, the power rule of integration would be, so basically you add the x, it's just like the total opposite. You add the exponent by 1 and then divide by the new exponent. You could also show it like this as well. Oh my God, what am I doing? You could also show it like this. But don't forget that plus C. Okay. The same thing with derivatives. A constant multiple can be taken out. There's the product, the sum and difference rule. This would be equal to, you can distribute an integral when you add or subtract. And that's pretty much it. And then basically you need to know like there's also, of course, the other special ones. Oh, God, I forgot to mention here. The power rule of integration only applies if n is not equal to -1. Okay, this rule works for any other exponent with the exception of -1. Why? Because if the exponent is -1, that's a totally different problem. This is like saying 1 over x, which is the natural log. Does it make sense? The derivative of the natural log is 1 over x. So you have to remember that. Of course, the antiderivative e to the x is e to the x. The basic trig ones, you should be able to go backwards from the basic trig ones. You should know all 6 trig and inverse trig. And that's it. I mean, that's pretty much all the, I mean, obvious. So it's very interesting. I actually have it at school. I don't think I showed you guys, but there's before like graphing calculators and all that stuff, actually my grandfather has a book because he was an engineer and he showed me. The derivative section of that book is like a few pages, right? It's like it shows like all the basic derivatives. That book is all integrals. Integral calculus is like there's so many rules and so many different formulas. It's insane. That's why you would need like a book to find other derivatives, other antiderivatives. These are the basics, and these are the ones you need to know. But obviously, there are so many other techniques you can use to solve these. In BC, you learn a few more, right? But in AB, these are the basics. You just need to know. You just need to know these. Okay. Um, Now what else was there? Then we talked about slope fields and differential equations, but that I think is better to go over with practice. So, because then you have to be able to separate the variables. So I'll give an example of a separation of variable one. So basically, if you're asked to find the let's say this, this way, sorry. Let me do it the other way. Okay, like this is called a differential equation, which is again basically an equation that has a derivative is a differential equation. The problem with this differential equation is that it's a function of x and y. So really the only way to do this is if you can separate the variables so that on one side you could integrate with respect to y and the other side you could integrate with respect to x, that would make everything so much easier. So really the trick here is multiply both sides by dx and then move anything that's y to the side with y and anything that's x to the side with x. You want to separate the variables, but again, dy and dx cannot be in the denominator. That's why, first of all, you would multiply both sides by dx. Right? Now you do not touch dy dx. Those are the limits of the variables of integration. So what this is saying is now anything that's y needs to go to the left, anything that's x goes to the right. So I'll divide y both sides. And there I go. This is step number one, separate the variables. If this was a free response problem, and free response, separation of variables, free response problems are like 4 to 5 points, really for all the steps that you have to do. So first multiply dx to both sides and then move anything y to the other side. Now the variables are separated and now you integrate both sides. And this sets up the problem so you could integrate the left side with respect to y and the right side with respect to x. So the left side would be ln of y, and the right side would be, well, you can think of this as just we could see 1/2 x to the minus 1. So we could say that this is 1/2 ln x. And then you have to put that plus c. The trick here is you don't have to put two constants. You just have to put one once you find the antiderivative. Okay. Then the last step is to solve for y, which again, you need to know. This is the hardest one. The reason I'm going over this is because this one's the hardest one because it involves logs, but the other ones are not as difficult. Again, the goal is to solve for y, but to get the y out of a log, you need to write it in exponential form. So you could think of it to do like e on both sides, right? Because you can do that, right? It makes logical mathematical sense. So with the inverse properties, you'd be left with then you could kind of break this up. So you have to know, again, your exponential rules. Like this is something that you need to know before calculus. So you could think of this as like, and this is important, solving for y is like now another important step because you're asked to solve the solution. So you're asked to find the function. So this here is a constant. So to make it look nicer, you could call it something else. So why don't we call it a, but we'll say that a is equal e raised to the c. But you can also, what else could we do? You could also do this. Right? And then that means this here would be x, and this means the square root. So this would be y is equal to a times the square root of x. So this is like the hardest one. Again, with separation of variables, you're going to get a lot of points on a free response, but you for sure are going to, you can get easily 2 points. Like for sure, you can very easily get 2 points just by one, separating the variable, and two, finding the antiderivatives. For sure, you got 2 easy points there. The rest is very algebra heavy. So that's where you get the other points from. Now, if you are given an initial condition, at this point, this is when you'd solve for the constant. Do not wait to the end to solve the constant. Right when you find the antiderivatives, solve for that constant if you have an initial condition. And that will be another third point, which is another easy point to get. So for sure, you can still, even though this is a little tricky, the hardest part of this is solving for y. But the first 2 steps should be very easy and very straightforward. Okay, so you should at least, with a separation of variable free response problem, get 2 points, at least. At least. There should be no excuse there. Okay. So that's like the basics of separation of variables. And then of course, slope fields are pretty easy. It's just like a little line segment representing the slope at any point. So you basically just have to kind of like use a little bit of logic there and figure out which slope field matches which differential equation. Okay, and that's it. Okay, so that's it for antiderivatives. Then we go into definite integrals, which first you had to know your Riemann sums. Okay. God, I just want to finish this. There's so much. I thought I could do this 1 hour. Oof. If I speed this up though, maybe I could like cut it and like speed it up and just have me speaking like really fast. And maybe that could be in an hour, but oh my God, I didn't realize how much information this was. I mean, because this is all fun to me. I love it. I think it's so much fun, but it's a lot. Okay, so let's see if we could finish this quickly. So of course, your Riemann sums is you basically try to fit as many rectangles under a function as possible. You can do left, right, or mid. Okay. Really, it's just base times height. That's really all it is. You get the height of the function times delta x, where delta x is equal to b minus a over n. So again, you have a function. You break this up into certain rectangles. And basically, it depends if you want to do right or left or mid. So the height of the function could be determined from the left side of each interval, right? It could be determined from the right side of each interval, or it could be determined by the middle value. So basically, you just have to play around with what value of x do you want to plug into the function to calculate the height. That's pretty much all the difference between left and right is. Now, the technical way now is like, if you're now adding a bunch of these rectangles, remember, you could express that as a summation. So you could basically say from 1 to n. You're basically going to add n rectangles together. Okay, so that's that notation. So The value of x that you plug into the function depends if you're doing left, right, or midpoint. So basically, if you're going to be doing left, it's going to be a plus I minus 1 delta x. Because again, if you're starting on the left, you're starting technically at a. So you don't start adding delta x until the second one. So that's why you're always like one step behind with adding delta x when you're doing left. If you're going to do right, you're starting first at the first delta x. So it's I delta x. And then for midpoint, this one is that. So that's basically your Riemann sums. Okay. And of course, you could also do trapezoidal approximation, which honestly, all you need to remember is the area of a basic trapezoid like this. We'll call this height left and height right. And then we'll call this delta x. So the area would be delta x divided by 2 times height left plus height right. Okay, this is for a trapezoid. And you basically just add all those trapezoids together. Okay, so that's like the basics of approximating areas. Okay, now the gag is if you make the number of rectangles approach infinity. See, this is where limits now comes into play, because now you have to conceptualize the concept of now making the number of rectangles go to infinity. So as you fit more and more rectangles, you will approach the exact area. And this is what we call the definite integral. Okay, so this then is the definite integral. Okay, and the further gag of this all is that this is related to the antiderivatives. This is literally the antiderivative at b minus the antiderivative at a, and that's the fundamental theorem. So that is how all of calculus is interconnected to each other. And this here, again, this is the fundamental theorem. Okay, so basically all antiderivative rules are applied to the definite integrals because you have to find an antiderivative anyways. So all of the antiderivative rules are going to apply. There are a couple of, or 3 definite integral rules you need to know, which are these. So basically from a to a, there's no area. If you flip the order, the sign of the solution changes. And of course, you can like add multiple areas together from, so basically if you do like from A to B, and then you add to that from B to C, this would be the same as the area from A to C. Right. So that would be that. So those are the basic definite integral rules. Okay. So that basically summarizes the everything about definite integrals, essentially. Again, there is technically a second part to the fundamental. This is technically part 2 of the fundamental theorem. Part 1 is if you think of the definite integral as a function, the derivative of that is just the function itself. So this is the fundamental theorem of calculus, part 1. And that's the main, that's an important one. Okay, so that summarizes definite integrals. And then the last part was applications, which was, what was I going to say? The net change theorem, which just states this is really just the fundamental theorem with application. So this here is just the net change of f from A to B. The total change would be this if you did the absolute value. This would be equal to the total change. Okay. And then what else? Then we had the area between two curves. So if this is f and this is g, and f of x is greater than g of x between A to B, then the area between these two curves would be and that's that. And then of course you had your solids of revolution, which I think the main formulas to memorize are this. Where C is equal to axis of revolution. Actually, let's say horizontal axis. If you're going to do a vertical revolution, you do it with respect to y instead. And then for disk method, for washer method, this is disk. For washer, same thing, it's just you're going to subtract two of them. That's pretty much all the disk. So it's just subtract two disks, essentially. And then the last one is the area between two functions, or the cross sections are shapes that are coming out of the function. So really all you have to do is the integral of the area as a function of x from A to B. And that's it. And that's it with calculus. Those are all the main topics. So, oh my God, finally done with that. Okay, finally. Do you have you are the last person standing.
And I'm tired too.
I know, it was a lot of information. I mean, was this helpful or should I have done?
Yeah, it was helpful. It was helpful. I'm glad how you summarized it. I feel like you covered everything.
Yeah. And we went through all the formulas and everything. The thing with calculus, with the AP exam, is these concepts themselves are not like hard by themselves. It's now just like interpreting the questions that they ask. And that's then where the AP practice comes from. So maybe let's do this. Let's take a break. I'll come back at 12:30. I'm going to send a reminder and tell everyone at 12:30, I'm going to do practice. And then from 12:30 to 2, I'll be here and we'll just do practice, whoever decides to come.
Okay, sounds good.
Okay, so that way go eat something, relax. So I'm going to send a reminder and let everyone know.
Okay, thank you.
I'll see you in a little bit then. Bye.